Hello students and welcome to a new lecture. In this lecture we will learn why certain groups why the elements in a certain groups have similar properties, meaning why does fluorine act in a manner similar to chlorine or bromine, or carbon will act like silicon and nitrogen will act like phosphorus. It has to do with the valence electrons and how many valence electrons are there. So what you are going to look at here is the following. If you look at carbon, the valence electrons is 2s2, 2p2. For silicon is 3s2, 3p2. And if you look at boron, it's 2s2, 2p1. For aluminum, 3s2, 3p1. Even further here in the halogens, for chlorine, for example, it's 3s2, 3p5, bromine 4s2, 4p5, iodine 5s2, 5p5, and so on. So not only the amount of valence electrons is the same, but it's also the same distribution inside the orbitals. So every element in a group 1A will have a valence electron configuration of ns1, n being whatever n, depending on the element, what is the highest n. Group 2A, ns2. Group 3A, ns2, np1, ns2, np2. For group 5A, ns2, np3. Group 6A, ns2, np4, ns2, np5, and ns2, np6. So for the B groups, the first row will be a D1, in the middle we're going to have a D5, and then we're going to have a D10. So it does make sense because the valence electrons are the ones responsible for interactions and reaction, that if I have the same valence electrons number-wise and configuration-wise, I should predict that elements in the same group will have similar properties. Okay, so here is a highlight for that. Look at group 1A and look how they have the exact same electron configuration. It is noble gas and then one electron in the next s orbital. Group 2A, they all have noble gas and then 2 electrons in the next s orbital, and so on. For the cations and the anions of representative elements, because of their similarity in the valence electrons, all elements in a group 1A will tend to lose 1 electron and therefore will have a +1 charge. Group 2A will have a +2 charge. Group 3A will lose 3 electrons to become like the previous noble gas and has a +3 charge. Group 5A will gain 3 to become like the next noble gas and have a -3 charge. 6A -2, 7A -1. Electrons are both attracted to the nucleus and repelled by other electrons. What does that mean? Think of an electron in an atom. It will be attracted to the center because the center is where the nucleus is and where the positive charge is. But also, it might have electrons around it that will repel it. So, therefore, there is a certain charge that the electron will feel depending on what is around it. Is it so close to the nucleus? Is it far away from the nucleus? Does it have too many electrons around it? And so on. So, in simple definition, the effective nuclear charge is the charge felt by an electron. So, here is an example. This is sodium atom. Sodium has 11 protons in the nucleus, 11 plus charge, and it does have 11 electrons around it. 10 of them are what we call the core electron and 1 valence. So the 10 electrons are in N1 and N2, and then the valence is the 3s electron. So that valence electron, how much charge does it feel? Does it feel the +11? No, because the +11 are almost cancelled out by the -10 electrons. So this electron in the 3s orbital will end up feeling only 1. And that 1 is what we call the effective nuclear charge. So how do I calculate that effective nuclear charge? It's equal the atomic number minus the number of the core's electron or the inner core electrons. So it is atomic number minus the shielding effect, which is the shielding constant, which is always bigger than 0 and lower than the atomic number. So the effective nuclear charge does have a trend on the periodic table. It does increase going up a group, and it does increase traveling from left to right on the periodic table. So let's look at that and try to understand why is that the case here. Because when you, in a group setting, within a group, what happens really that when we are up at n equals 1, right, that electron is definitely closer to the nucleus than n equals 5, for example, right? So of course that electron here will feel more charge and attraction than an electron in the s orbital here. As I travel across the period, what happened is that the core electrons number remain the same, but the atomic number increases. And remember that this is calculated by atomic number minus the core, the shielding. So as you travel in this direction, this number stay constant because the core does not change, because I am at the same n level, and the core will only change when you change the n level. But the atomic number increases. So, as a result, there will be more positive than negative canceled, and therefore electrons will be feeling more attraction. So, as I go from group 3A to group 4A, the valence electrons here in 4A will feel more attraction to the nucleus than the electron here. And that will affect the first property that we will talk about, which is the atomic radius. Atomic radius, by the definition, or the size of the atom, if you don't want to be fancy about it, is half the distance between the two nuclei in an adjacent atoms. So if you have these two atoms, and the radius here will be half this distance right here. Let's change color. That distance right here between the two nuclei, half of it is the radius of the atom. And the radius is an expression and a measurement that allow us to have relative size of the atom. So if we look here, this is a really nice three-dimensional representation of the periodic table. And what is trying to represent to you is the relative size of the atom, the radius of the atom. If you see that the radius does increase when we go down a group. So if I try to go here with one direction, like this one here, do you see how the atom is increasing as I am going down the group, regardless of where you go? So the size does increase going down the group. And it looks also like, generally speaking, with a few exceptions though, that the size is decreasing when I go from left to right, which put helium at this corner to be the smallest atom we know. Helium is smaller than hydrogen, and will put that corner to be the largest atom we know. So, what we know so far, that the larger radii, stronger hold of the nucleus on electrons, and therefore a smaller the atomic radius. So, as I am going, if I want to now make a link between the effective nuclear charge and the size, Because when I go down the group, right, and I will show you beautiful pictures to explain that principle, the electrons get further away from the nucleus, right? Because this is like a smaller atoms here, but when I go to N2, it gets bigger, N3 even bigger, and bigger and bigger. So it does make sense that the size will increase going down the group. Now, why would the size decrease going across a period? Because remember how the attraction of the electrons, right? So all these electrons are at the same n level. However, if this electron is experiencing more attraction than this electron to the nucleus, then the atom will shrink. Those electrons are gonna come closer to the nucleus, and that explains why the size decreases going left to right on the periodic table. So across the period, number of protons does increase, but it's the same shell of electrons, and down the column the shell size increases, and that explains the size. So now let's look at this. This is beryllium. We have 4 protons in the nucleus, and then you have 2 electrons at the first n level and 2 electrons at the second n level. Now, when I go down the group, look at what's happening here. I start to add electrons to the next n level. N3 is even further away from N2, so naturally magnesium has to be larger than beryllium. And then if you go to calcium, the last electrons are n equal 4, which is even further away from the nucleus. Naturally, calcium is larger than magnesium when it comes to the radius. Now, let's walk across a period. This is period 2. All of them has the valence at the same last n. So, lithium has the last valence at n equal 2, and the effective nuclear charge for that valence electron equals 1. Beryllium, on the other hand, the effective nuclear charge here will equal 2. So what does that mean to you? You see these electrons here feel more attraction to the nucleus, and therefore that will shrink the atom, make the n level get closer to the nucleus. As a result, the radius is smaller. And as I keep going, it gets smaller and smaller because the effective nuclear charge keeps getting higher and higher and higher. So these electrons are attracted more and more and more to the nucleus. So neon is the smallest element when it comes to period 2. Now let's practice problems, and you definitely need to look at the periodic table in front of you to answer those questions. Put in order of decreasing atomic radius. And the first elements that we're having phosphorus, we're having silicon, and we're having nitrogen. It is very hard to compare 3 things at once. So what I like normally to do, I like to compare things first, 2 elements to each other, and then the winner of that will go and be compared to the third one. So in the periodic table, nitrogen is definitely above phosphorus, and silicon will come to the left side of phosphorus. So now when you look at this, we know that between these 2, right, who is smaller? Well, we know that nitrogen is up, so nitrogen has to be smaller than phosphorus, okay? And between these 2, who is smaller? Well, clearly, when we go across the period, the size does decrease. Phosphorus is smaller than silicon, and nitrogen is smaller than phosphorus. So if I am putting them in order of decreasing atomic radius, it seems like the largest is silicon, then silicon will be followed by phosphorus, then nitrogen. Nitrogen will be the smallest. Now let's look at these: carbon, lithium, and beryllium. Now on the periodic table, we have lithium, then we have beryllium, and then at one side here, you're going to have boron, and then after boron, you're going to have carbon. So we know that they are all at the same end level, and sizes decreases going this direction. So what does that mean to you? That lithium is larger than beryllium and larger than carbon. Okay, so here is the periodic table one more time, and you can see that the relationship here that I just have stated between these three here, nitrogen, phosphorus, and nitrogen, and silicon. And here you can find the, let me have a different color here. So here you can have the carbon and lithium and beryllium. All right. Now, what about the radius of ions? All the radius that I just talked about and discussed are radiuses of a neutral atom. But when I have ions, whether they are positive charges or negative charges, I need to take into consideration that cations are smaller than the corresponding atom, which means a cation is smaller than the neutral atom, right? So here it is. Look at this picture. A sodium cation is smaller than a neutral sodium. And excuse me. Look at the electron configuration of a neutral sodium. It's neon and then 3s1. Now, when it comes to sodium cation, right? A sodium cation will lose this electron here, which means it will be only left with neon, and neon is in the previous n level, so naturally the sodium cation will get smaller. So the cation is smaller than the neutral atom because it often loses its outer shell. The nuclear charge remains same, but you do have fewer electrons, which means that the attraction and the charges that those electrons will be feeling will become much stronger. Sorry, this is here, guys, fewer electrons. Let me write it down for you. Okay, the anions are larger than the neutral atom. So if you look at this picture, you will find that a chloride is larger than chlorine, right? And if you look at the configuration, I didn't do anything except that I added an extra electron to the last orbital. And what would that do, guys? Like if you are, just like try to envision a very simple picture of the atom. If this is the nucleus, and I did have my electrons here, and that atom was happy with those 5 electrons, and then there are the 2 electrons from the s orbital, and now all I did, I just added, this is a very simple picture, this is not how they look like, I brought to that valence an extra electron, so that will shake and shock the atom, because these electrons, they, if I gonna like color code them, I'm trying to just really speak simple terms here. These electrons, let's just put these 2 electrons as an example, we're kind of used to having that separation between them. All of the sudden, I introduced another electron in the middle. And what would that do? It will create a repulsive interaction. So these electrons will even go further out, and that will expand the n level and make the atom to be larger. Nuclear charge remains the same, but you have more electrons, and therefore there will be more repulsion. So generally speaking, the neutral atom is in the middle. An anion will be larger than a neutral atom, and a cation will be smaller than a neutral atom. So if you have lithium and fluorine reacting with each other, because it's a metal and non-metal, lithium, how do I know? Like, let me make it this to be a quiz question. If I did this, I didn't even show you what these elements are. Imagine you can't see anything right here. I told you this picture represents a metal and a non-metal reacting with each other. Which sphere represents the metal and which sphere represents the non-metal? How would you know? Well, you should say that the metal will lose electrons and become a cation, and the non-metal will gain electrons and become an anion. The green sphere, what happened to the green sphere? It did shrink, which means it became a cation, which means that must have been the metal. And what happened to the red sphere? It expanded, which means it gained electron, so this must have to be the non-metal, right? And now if I erase this here, you will see that this is correct. The green sphere was corresponding to the metal, which is the lithium, and the red one was corresponding to the non-metal. In this case, it was the fluorine. Now, if you look at this picture, you will see that the gray sphere represents the neutral atom. The pink represents what happened to the cation. And if you can see that the pink is smaller than the gray. So let me highlight things for you. So this here, the yellow represents the potassium cation, while the gray portion represents the neutral potassium, okay? The yellow here represents the magnesium cation, while the gray represents the neutral magnesium, and so on. Now, if I look at the other side, the gray here is the neutral chlorine, but when it gains an electron and becomes an anion, it becomes the blue sphere. So the blue sphere represents the larger anion. So now let's compare ions to each other. If the ions are in the same group, going down, and if they have the same charge, then going down the group, it will increase the size. Size of the shell increases as you go down a group. So what does that mean? Let me show you some examples here. So you can have a lithium cation, sodium cation, right? And cesium cation, right? And this is going down the group in group 1A. And they are all cations, but if I compare them to each other, as I go down, I am increase the n level. So cesium is larger than sodium cation, larger than lithium cation. Now, there is also something that's called isoelectronic ions, which means these are ions that have the exact same electron configuration. It decreases as Z increases. So what does that mean? As the atomic number increase, the size will decrease because you're going to have a larger effective charge. However, the most positive charge will be the smallest, and the most negative charge will be the largest. So here is an example. These ions, what they have in common, guys, are electron configuration. They all have the same electron configuration, which is the electron configuration of the argon. However, if I want to organize them or arrange them based on their size, -2 charge on sulfur will be way larger than -1 on a chlorine. And then the negative is always larger, anions are always larger than cation. And a +1 is larger than a +2. So the higher the positive charge, the smaller the atom. And the higher the negative charge, the larger the atom. All right, so now let's predict which one has a larger radius. If you have a fluoride and a nitride, right? So these two are here, fluoride and a nitride. They all gonna be isoelectronic with neon. So the more negative, the larger. So nitride should be larger than fluoride. If I have magnesium and calcium and they both have the same charge +2, if you go down the group, the atom get larger. So calcium +2 is larger than magnesium +2. Iron 2, iron 3, that's easy, it's the same atom. The higher the positive charge, the smaller the atom. So iron 2 should be larger than iron 3. Sodium +1 and magnesium +2. These are, I'm gonna erase this here for a second. And these here are isoelectronic with neon, right? So what I know is the higher the positive charge, the smaller the atom. So sodium cation will be larger than magnesium cation. Calcium and calcium +2, I know that for any given atom that the neutral is larger than the cation. So calcium is larger than calcium cation. Chlorine and chloride, for any given atom, the anion is larger than the neutral atom. Now, the next trend on the periodic table is something that we call ionization energy. What is ionization energy by definition? Ionization energy is the minimum amount of energy required to remove an electron from a gaseous atom in its ground state. So when you remove, what does that really suggest? That removing an electron to make a cation does cost energy. And that energy is called ionization energy. There is a requirement, though, that the atom has to be in a gas state. Larger value of ionization energy suggests that it is more difficult to remove that electron. So here is how we look at it. If I have X atom at a gas state, I have to add a certain amount of energy to remove that electron and make a cation. And that energy is called ionization energy, or the first ionization energy, right? First ionization energy. Now, first means the ionization energy that needed to remove the first electron. Why? Because I can remove another electron from the first cation. So if I add the second ionization energy to the first cation, then I'm going to get a +2 charge and I'm going to lose that second electron. That is called second ionization energy. Now, a third ionization energy is to remove a third electron from the +2 cation, and that is called the third ionization energy. Now, the first electron is the easiest to remove. Then after that, it becomes harder and harder and harder, meaning higher energy, because now you're removing an electron from an atom that has more protons than electrons. So the attraction to the nucleus will be very strong, and it will become much harder to remove that electron. So for all atoms, no exception, the first ionization energy will be lower in value than the second ionization energy, which is lower in value than the third ionization energy. Now let's look at this diagram together. I'm going to show you how to identify what we call a jump in ionization energy. For sodium, the first ionization energy is 495. But look what happened to the second one. It has a huge jump. Why? because now the second electron is being removed from the core. The first was from the valence. So remember, sodium has only one electron in the valence. So removing the valence is easy, but the core is hard. So for sodium, I see the jump happening in the second ionization energy, and for a good reason, because this is where the core starts for sodium. Now look at magnesium. The first two, there is no huge jump between the 738 to 1451. But look what happens to the third one. Huge jump. Why? Magnesium has two valence electrons. The third one comes from the core. Aluminum has 3 valence electrons, right? So it will be 1, 2, 3. The fourth is coming from the core, so you see there is a huge jump. So I always can, from the given values, I can always identify where the jump happens, which is the first time I leave valence electrons and I start to remove core electrons. Now, there are a couple of exceptions in the chart for first ionization energy. So I want to first bring your attention to the fact that I am looking at first ionization energy, right? And I also want to bring to your attention here, I'm going to put a periodic table, and I want to show you where the exceptions are. So if you see here, this is lithium, right? And then beryllium. So lithium, beryllium. And then for the next one is boron. And instead of boron going higher, it has a dip here. The next dip is between, so after boron, we get carbon. So this element here is carbon. Then we get nitrogen here. And then instead of oxygen going up, we have a dip. So why is that the case? We have to look at the electron configuration to understand. Lithium is 2s1 electron, right? Then we have beryllium, Beryllium is 1, 2, 2s. And then we have boron, which is 2 electrons in 2s and 1 electron in 2p. It turned out that removing these electrons here is much easier than removing this electron from beryllium. Why? Because remember how when beryllium had that full 2s orbital, which provides some special stability. So when I remove that electron, it disturbs the stability, and it's going to cost me higher energy than removing the first electron from boron. So these are the exceptions that we have to deal with. The second exception, let's do nitrogen and let's do oxygen. For nitrogen, I have 2s and 2p. And oxygen, I also have 2s and 2p. And for nitrogen, 1, 2, and then 3, 4, 5. For oxygen, 1, 2, 3, 4, 5, and 6. Now, removing this electron will be much harder than removing this last one. And the reason for that, because removing the one from the nitrogen will disturb the half-filled p orbital, while removing the one from the oxygen will create the half-filled p orbital, which has a special stability. So what is the trend of ionization energy on the periodic table? The larger the effective charge, the more difficult to remove the electron. Therefore, it decreases down a column. So larger atoms that are further away from the nucleus, it's easy to remove that electron from them. And we talked about the two exceptions for the first ionization energy between group 2A3A and 5A and 6A. Okay, so now look at the trend on the periodic table for the ionization energy. The trend is pretty clear here, and the exceptions we talked about are also straightforward. You can see that ionization energy decreases as I go down the group, and generally speaking, you can say increases across a period, but see, here is the exception between oxygen and nitrogen, and the exception between beryllium and boron. The ionization energy is also associated with the metallic character. So the more metallic character, the more the element exhibit physical and chemical properties of a metal. So when I said, what do I mean by the metallic character? It means how much does the element look like a metal, okay? So reactive metals lose electrons easily, which means they have low ionization energy. So the lower left corner of the periodic table is where I have the most metallic character of the elements. So the lower the ionization energy, the more metallic character I have. And if you look at this periodic table trend, you will see that the lower left corner of the periodic table is where I have the most metallic character for my elements. Now we're going to look about or at something else that's called electron affinity. Electron affinity is simply delta H that should tell us the heat. It's a heat of a reaction that will tell us how strongly an atom loves to gain that electron. So energy changes, that which is delta H, that occurs when an electron is added to the gaseous atom. The atom has to be in the gas state. So if I add an electron to X atom at a gas state to become an anion, and I calculate delta H for this step, then that is the electron affinity. Now, fluorine loves to gain an electron, and therefore it's such an exothermic reaction with a high negative value. The more negative delta H, it means the more the atom likes to gain that electron. Now here is a table that shows electron affinity, and you can tell here that halogens have high electron affinity. They love gaining electrons, and at the top there, fluorine is the most electronegative atom on the periodic table, right? Now, why is that value very, very positive for noble gases? Noble gases do not want to do anything. They don't want to gain electrons or lose electrons. So it's going to cost a lot of energy to disturb their stability, whether by losing or gaining electrons. Generally speaking, you will see that these values do become less and less and less negative when you come to this side of the periodic table, because these are metals, and if anything, they like to lose electrons rather than gaining electrons. So this is the trend of electronic affinity, and it is the highest, going from left to right and going up a group. Now that will allow me to talk about electron negativity. So we did see ionization energy, which is a measured value, and we saw also electron affinity, which is another measured value. Now when I look at electron negativity, it's simply the ability of the atom to attract electrons once bonded in a covalent bond. Covalent bond is about sharing electrons. However, atoms don't share equally. Some of them will be stronger, pulling those electrons closer to them. And that's because they are very electronegative. So electronegativity is the ability of the atom to attract electrons in a covalent bond. The higher the electronegativity, the greater tendency to attract electrons. And those values of electronegativity are combination of the two measurable quantities that we looked at, which is electron affinity and ionization energy. Now, this is a beautiful diagram here on the periodic table, and it highlights that the highest electronegative atoms are nitrogen, oxygen, fluorine, and chlorine, fluorine being the most electronegative atom on the periodic table. And as you saw in the previous slide, it has the highest electro-affinity when it comes to gaining electrons, the heat that evolved when gaining electrons to the gases atom. That's it for this lecture. I hope you enjoyed it, and I will see you in the next chapter.